Good morning, everybody. Again, I'm Francesco Maria Puglisi, and I'm starting now my third year as a PhD candidate in this international doctorate school. And I focus my work on random telegraph noise analysis and compact modeling of hafnium oxide-based resistive random access memories, especially in one of the two operating conditions, which is the high resistive state. And during the last year, I focused my work on the analysis of complex multi-level random telegraph noise in these emerging devices, mainly to understand or validate or to enhance the actual understanding of the conduction mechanism and the origin of the random telegraph noise itself in these devices. And I successfully related the RTN statistical properties to the property of the conductive filament, which is one of the constituents of these devices. And I carried on an advanced characterization of multi-level random telegraph noise, successfully inferring the characteristic of the traps causing the random telegraph noise itself. And I highlighted the relation between the reset conditions, the properties of the conductive filament, and the random telegraph noise itself in the unified framework of the trap-assisted tunneling conduction mechanism. So this is a brief outline. I will introduce the object of my talk, which are hafnium oxide-based resistive random access memories. I will show you a couple of experiments I carried on, and I will introduce the modeling activity I did. And I will show you some results about random telegraph noise and the statistical properties of the conductive filaments and their statistical relations, and then conclusions follow. So here the reason why we are focusing our activity on these devices, and that's because they are really powerful alternative non-volatile memories. They have a very simple structure, basically an oxide layer sandwiched in between two metal electrodes, so high integration possibilities. They allow very fast switching, even below 1 nanosecond, and they allow low power operation, excellent memory characteristic, high endurance, high data retention, high memory window. Moreover, they are fully compatible with the actual backend of line of the CMOS process, so they are ready to go to be easily fabricated. But of course, there are some shortcomings or open issues. First of all, the material instability, which is to say these oxide layers are very unstable and not widely known till now. So this also causes a considerable device-to-device variability, which is an actual problem for the full industrial exploitation of the ReRAM concept itself. And moreover, a full, complete knowledge of the physics of conduction and switching of these devices is still missing. At least a unified framework is missing. And from a practical point of view, huge random telegraph noise fluctuation appears during the readout operation, possibly leading to the failure of the read operation, which is critical for memories. So the purpose of studying noise in these devices is twofold. On the one hand, we want to understand its origin, to validate the actual understanding of the conduction mechanism. On the other hand, we want to investigate this noise to give hints to technologists on how to reduce the impact of the noise itself. So now I will show you the main experiments I carried on during this year. We repeated 100 consecutive full switching cycles, each of which is composed of a set operation driving the device to the low resistive state, which is the right part of the butterfly curve. You can see it on there. And a reset operation, which is the left part, the negative voltage ramp that you see on that butterfly, setting the device to the high resistive state. And then in this state, we also performed a readout operation, which is simply current sampling over time to retrieve RTN information. Basically, we repeated this experiment for 4 different reset conditions, namely 4 different reset voltages, where the reset voltages is highlighted down there, and is the maximum absolute value of the voltage during the negative voltage sweep. And that's a very important parameter, which can be used, can be swapped to define different high resistive states. Now I have to introduce some ReRAM modeling activity I carried on. First of all, I will show you a compact IV model, which was winning the Best Student Paper Award at international conference sponsored by IEEE, and that's basically it. You can see a schematic depiction of the states of the device in different operating conditions. In A, you find the pristine state of the device, so basically the oxide layer itself. After a preliminary forming operation, which is used to enable resistive switching in these devices, a conductive filament is created, the blue cylinder, setting the device to the low resistive state. In this state, the conduction can be approximated as quasi-ohmic, and its resistance can be expressed in that way with the first equation. That's a really simple but powerful equation, since through simple IV measurement we can estimate S, which is the cross-section of the conductive filament, which is the most important parameter, since the resistivity of the conductive filament is widely known in the literature, and also the thickness is just the physical thickness of the oxide layer. So through simple IV measurement we can estimate at each switching cycle in low resistive state the cross-section of the conductive filament. On the other hand, when we apply a negative voltage ramp, the bottom end of the conductive filament gets dissolved, and a dielectric yet defect-rich barrier is formed in its place, which is the orange part, and its thickness is related to the reset condition. So the higher the reset voltage, the thicker the barrier, the higher the resistance in high resistive state. So the reset operation drives the device to the high resistive state, and that's basically the formula we can use to estimate the resistance, and is made up of two contributions. The first one is the remaining part of the conductive filament in blue, and the second one is the resistance of the dielectric barrier, which is formed during the reset operation, and everything is linked to X, which is the thickness of the dielectric barrier. So again, simple IV measurement allow us to retrieve experimentally the value of the resistance and then to estimate the thickness of the dielectric barrier. This can be repeated easily at each switching cycle. So for each switching cycle, we can estimate the properties, the physical properties of the conductive filament, both the cross-section and the thickness of the dielectric barrier you can see down there. This model is also very powerful since it can properly catch the temperature dependence of the conduction mechanism, which is the trap-assisted tunneling, and has been verified with physics-based simulations. And as you can see, the accuracy is quite high and the computational burden is extremely low. Also, since we are dealing with readout operation, I have to introduce the random telegraph noise model that we are using to analyze complex fluctuation. First of all, random telegraph noise appears as an abrupt switching of the reading current between discrete values and is mainly thought to be ascribed to the activation and deactivation of traps, defect centers, within the barrier acting as conducting sites or traps, allowing the charge carriers to flow from the tip of the remaining part of the conducting filament to the bottom electrode. And the simplest form of RTN you can face is the so-called two levels RTN, and is ascribed to the activation and deactivation of a single trap. And that's the result. So we have two discrete levels, and the current is randomly switching in between these two levels. With this kind of situation, it's quite straightforward to define some statistical properties of the signal which are directly related to the physical properties of the trap. And they are the amplitude of the fluctuation and the average capture and emission time. In this case, it's quite straightforward, so we can directly analyze the physical properties of the trap starting from this signal. However, in these devices, we face a way more complex kind of RTN, which is the multi-level RTN, which is thought to be due to the simultaneous activity, activation and deactivation of multiple traps within the barrier. And now the fundamental question is this: can we separate the single trap's contribution starting from this kind of signal? In other words, can we simultaneously assess the physical properties of all the traps contributing to random telegraph noise starting from this kind of experimental signal? Actually, the answer is yes. And it's possible if we consider that in these devices, multi-level RTN can be seen as a superposition of different independent two-levels fluctuations. So this signal is seen as the summation of independent two-levels fluctuation, each of which is related to the activity of a single trap. So in this fashion, and you can check also this reference for details if you're interested into, with this model in mind, we built a mathematical model to extrapolate this information and is based on a refined implementation of the hidden Markov model, which is called the factorial hidden Markov model. Basically, the system generating the RTN, whichever it is seen as a superposition of independent Markov process. Each Markov process, each Markov chain, each row, is associated to the activity of a single trap. So the output of the system at each instant of time, which is the expected value of the multi-level RTN, is actually due to the superposition of the states of many Markov chains, each of which is related to a single trap. So each Markov chain state at each instant of time can assume one out of only two values, since each row is related to a two levels RTN, which is related to a single trap. With this kind of model, we can actually decompose the multi-level RTN into single two levels fluctuations, and we can simultaneously analyze the physical properties of each trap. And that's the basic result. That's the experimental data, and that's the FHMM fitting. Only with this kind of implementation, it is possible to see this signal as the superposition of trap 1 and trap 2. So we can easily study and assess the physical properties of each of the traps. And with the actual implementation I used, the number of traps contributing to RTN is automatically spotted. So we can know at a glance how many traps are contributing to RTN and their physical properties, thanks to the knowledge of the amplitude of the fluctuation and the average capture and emission times. And here are some basically results that we can have exploiting this kind of analysis for consecutive switching cycles. Here we can see a statistical relation between the number of traps contributing to the RTN and the reset conditions. As you can see, regardless the reset voltage, we can face very complex RTN due to 4 or 5 simultaneous activating and deactivating traps, but also very simple noise, for example, given by one trap or zero trap, which is only Gaussian noise. So there's no point-to-point relation between the reset condition and the complexity of the RTN itself. Yet a statistical relation emerges if we look at these results over multiple successive switching cycles. Indeed, as you can see, for low reset voltages, most of the times the RTN is quite easy to analyze, one trap or two trap, but as reset voltage grows, also the noise complexity grows, and we can define a statistical figure of merit for noise, which is the effective number of trap, simply the mean, the integral mean of these curves. We can also perform a kind of statistical analysis for the conductive filament properties, exploiting the compact model I showed you before. And here we can see some distributions of experimental values of the reading current, which are perfectly in line with the trap-assisted tunneling. You can see also the details in the reference at the end of this presentation. And the main point is that with simple IV measurement, at each cycle we can extract the barrier volume, which is the cross product between the cross-section and the barrier thickness itself. So again, we can define a statistical figure of merit for the conductive filament properties, which is the average barrier volume. Now, the funny thing is that if we cross-correlate the results, we can see that both the noise complexity, which is the effective number of traps, and the average barrier volume are growing with the reset voltage on average. So this is our average result over 100 consecutive switching cycles. And this relation is quite important because it says to us that noise is mainly ascribed to traps within the dielectric barrier, which is a very important result. And also, this kind of statistical analysis allows us to perform an accurate analysis of the conduction mechanism leading to noise. For example, here we analyzed the amplitude of the fluctuation over successive switching cycles in different reset conditions. And in this case, you see that the distribution is always log normal with always the same slope, meaning that the conduction mechanism is independent of the reset condition, is always the same. And again, that the main cause of the noise, the main root of the random telegraph noise, is the trapping and detrapping activity in traps within the dielectric barrier. And this is perfectly in line also with the multiphonon trap-assisted tunneling model that we use in physics-based simulations. So, concluding, I implemented successfully an advanced and refined implementation of the hidden Markov model, the factorial hidden Markov model, to study complex multi-level random telegraph noise. I developed a compact IV model which can be used to extrapolate the physical properties of the conductive filament, and I cross-correlated these results. No point-to-point relation between noise complexity and barrier arises, but a statistical relation between them is kind of clear when we look at their behavior over successive switching cycles. And a linear relation in particular is found between the reset voltage, the barrier thickness, and the number of traps on average contributing to the RTN, and everything is encapsulated in the multi-phonon trap-assisted tunneling physics model. So, thank you. This is partial publication list. You can check this reference for details if you wish.
So about the noise modeling, is it, I mean, random telegraph noise is a very old model. Is its application novel, or?
Yes, actually, the main problem is that random telegraph noise is quite known in standard devices, for example, MOSFETs, in which it's kind of simple since the interaction is between the channel or the substrate and the oxide layer. Here, the conduction through the barrier leads to unavoidable random telegraph noise, which is due to multiple traps, and the extrapolation of information from multiple traps is not that straightforward. And also, the relation to the physical properties is kind of difficult because the model we have to use to model the conduction mechanism is kind of complicated because it's a multi-phonon trap-assisted tunneling model, and joining the two things together was not straightforward. It's actually a very, very novel thing.
Okay, thanks again.